examples. I just want to talk about this idea of normal distribution. There's two examples of this that we're going to be dealing with. Right? We're going to be dealing with situations where we're looking at an entire population, and when we move forward a week or two, we're going to start dealing with samples and the way that they're distributed. They're also kind of normally distributed. But for this week, we're dealing strictly with populations. So if we were going to look at a population, we'd say to ourselves, okay, what's the average? And we came up with a lot of stuff already tonight. What's the average blood pressure for all the people in this population? And we decide it's 100, right? Well, if we then say to ourselves, well, what does that mean about the way that the blood pressure is distributed in this population? Well, not everybody's going to be 100, obviously. In fact, there may be very few people that are exactly 100. That 100 is an average. Half the people are below 100, half the people are above 100. In a perfect normal distribution, the distribution is symmetrical. Exactly half are below, exactly half are above. Now, we rarely run into a perfect normal distribution. And the basis for a normal distribution is chance. The only thing that determines whether you're on the left side of the mean or the right side of the mean when we select people at random is going to be chance. I got lucky, I got somebody above, got unlucky, got somebody below, so on and so forth, right? So it's strictly based on chance. There's a lot of other things besides chance that influence how things are distributed. If we were talking about height, right? Well, there's a lot. If the average height is 5'7", males and females combined, well, let's see, half the people would be below that, half the people would be above that. Well, maybe that's not quite true. Well, maybe it's not quite true. Maybe the median height is a little different than the average height. So it's not really a perfectly normal distribution. Maybe there are more shorter people than there are taller people. So it's kind of a skewed distribution, right? So all the rules we're going to talk about tonight apply to a perfect normal distribution. We rarely see a perfect normal distribution, but we often see distributions that are good enough that we can apply these rules and get a lot of good information out of them. And we're also about to learn why we bothered with all the stuff that we did before with the median and the mean, and why we went through such convolutions to calculate the standard deviation, taking up the sum of squares and dividing by the n-1, why we got that number and how we're going to apply that number. Those numbers, the mean and the standard deviation, are going to tell us an enormous amount about a population's distribution if we assume that it's normal. Again, we may swallow our pride a little bit and say that we'll be satisfied with reasonably normal, not perfectly normal for now. When we start getting into samples, we're going to find out that, in fact, things don't have to be perfectly normal to make these tools very useful anyway. So for tonight, we're dealing with population. So I'm gonna draw a sample distribution over here, and all this is based on the fact that if we were to put on a number line, create a histogram, well, in the middle, the place where the average is and the median is going to be the tallest bar of our histogram, and the next to that is going to be a shorter histogram, and a shorter histogram matching that one roughly, assuming it's a perfectly normal distribution, and so on and so forth. As we get further and further away from the mean, the frequency, the number of people that are in that population that are at that blood pressure or that height, let's say this is blood pressure of 100, then we're down to 80, and over here we're up to 120, right? The number of people are fewer and fewer that fit into each of that histogram. If I make those spaces small enough, I wind up with a curve. What comes out, our histogram, it's a big enough population, I have a large enough number of people in this population. Eventually, if I make these bars narrower and narrower, I eventually wind up with a curve that looks something like this. There's actually a formula that represents that normal distribution. I'm going to show you that formula for a second. There you go. There's the formula. So what's in that formula? See if I can make that bigger. What's in that formula? Well, f of x, that's the height of that line, right? The f of x is like the y-axis. the height of that line at any given point is equal to the mean minus, the value that you're interested in, like blood pressure at 98, right? Minus the mean over the 2 squared over 2 times the standard deviation squared. That's the power that we take this part of the function to, and that has sigma, which is the standard deviation in there, right? So everything that's in here, we can deduce from the mean, from the standard deviation, and from the value that we're interested in. So that's what determines the height of that line. Yes?
Is this for information's sake?
Absolutely for information's sake. Once I turn this off, never forget it. Forget you've seen it. Take it completely out of your mind. But the fact that there's a formula here means that someone can take that formula and they can make up a table for every possible value for us. That's called a Z table. We're going to start working with that shortly. But this is where that Z table comes from. We never have to look at that formula again because we're going to use the Z table. Okay, I'm going to give you another example of something that's normally distributed, but it's a binomial distribution, right? It's two things, kind of a yes or a no thing. Remember we did the probability tree with flipping a coin, right? How many heads we might get, how many tails we might get. And in the middle, we get the most frequent outcomes. And I'm going to show you a machine. This is actually the Queen's Hall of Science. So I can't get it to show up here. This is called a Galton machine, and it represents a binomial distribution, which approximates a normal distribution. We're not going to worry about that right now in terms of what that means, but I just wanted to show you how this thing works. There's music. Okay, so I'm going to go space through this quickly. There's a little hole at the top of this thing, right there, and it's dropping steel balls down into these little pegs. Anybody ever see a pachinko machine? Know what a pachinko machine is? It's like a Japanese kind of pinball machine. It's kind of like that. They're dropping a ball right down the center, and it's going to hit a peg here. Those pegs are aligned, so basically it's a 50-50 shot. Could go to the left, could go to the right, right? So when it hits one peg, it bounces off and hits the next row of pegs, and the next row of pegs, and the next row of pegs. So if there's a line of 10 rows of pegs, how many times would we expect it to go to the left, and how many times would we expect it to go to the right? 50-50, right? 5 times to the left, 5 times to the right. So we'd expect the balls to line up mostly in the center, right? And as we get away from the center, it'd be unusual to see a ball go 10 times to the left or 10 times to the right, right? So let's see if that works out here. You can see them coming down, bouncing off the pegs. Okay, we got a close up there. Here we go. Let's go down to the bottom. Then there's people standing there looking at this for like hours. Trust me. Let me make it. Okay, here we go. And as they fall into tubes at the bottom, and we can get down to where they're collecting, sure enough, there's our distribution. How cool is that, right? Right? So there was, when I took this film, there was one kid that was sitting on the floor behind this thing, and he was determined to stay there until it filled up so he could see it flush out. So at any rate, but that's a form of a normal distribution. Happens to be it's an approximation to a normal distribution because it's really binomial. There's a little difference. You don't have to worry about that difference for now, right? But you can see that in real life, chance takes this kind of the nature of this thing. It actually does work that way. So I'm going to open up an exercise document that's on Blackboard. That you can watch it on here, or you can follow me on your computers. Okay, there's actually a version of this that I actually put the answers into as well. Okay, so I don't know what it is. It never asks me for an update until I'm in this class. You hide the ribbon here so I get a little bit more room. Okay, so here's our normal distribution. As it happens, based on that formula that you just saw, as you were talking about in class, this has a certain quality to it That's always true for all normal distributions. Now, you can have some distributions. Let me just, I'll start with this one for starters. Yeah, in a normal distribution, we know it's symmetrical. So we know right away that if I have the mean in the middle, half of the population is to the left, half of the population is to the right. You could look at this another way also. You could look at this as probabilities. What's the probability that if you select one person in this population at random, that they'll be to the left of the mean or to the right of the mean? So you could look at this as 50% chance the person will come from the left of the mean, 50% chance the person will come from the right of the mean, right? You can actually say, well, let me block this out. That's the probability, what's left in this area over here. I block out all the people above the mean. That's the probability that I would pick someone from that section of this curve, right? So now, okay, that's great. So now, what about if I want to look at this, for a different, this is a very interesting looking distribution. Okay, what about if it has a different shape, right? We can have a normal distribution that looks like that, but we can have a normal distribution that looks like this. And we can have a normal distribution that looks like that. They're all bell-shaped curves. They all apply that formula. What's the difference? The difference is the mean, right? In one case, it might be the same number or a different number than this distribution. And really, the way that they're spread out, whether they're tall and narrow or flat and wide, the difference is the standard deviation. Whenever I use sigmas, I'm talking about the standard deviation of the population, by the way. If I use SD, I'll talk about sample, right? So what's the difference between this, and this is really the spread, the way it's spread out, the standard deviation. So in each of these, 50% of this population is to the left of the mean, right? It's true in every one of these things. Doesn't matter because the mean's always in the center. What's a little less obvious is that 95% of all of these populations, whether it's this one, or this one, 95% of these populations is between two standard deviations below the mean and two standard deviations above the mean. Same is true for all of them, except it's their particular standard deviations, right? And so on. That's true for all normal distributions. Now, notice I didn't say that someone with a blood pressure of 80 is two standard deviations, or the range for 95% is not 80 to 120 or 82 to 105 or something like that. I described it in terms of standard deviations. That's why standard deviation is such a powerful tool, right? So one of the rules we have is 95% of the population is between two standard deviations below and two standard deviations above. So now if I told you that our mean was 100 for this particular standard distribution, our mean, mu, is equal to 100, right? But I told you the standard deviation was equal to 5. What's the range for 95% of our population? Where would that be? Two standard deviations below the mean and two above. So standard deviation is equal to 5. So 95% of this population is going to be between 90, right? 2 times 5, and 110, right? Okay, what if the standard deviation instead of 5 was 15? What would it be then? It'd be 30 below and 30 above. So it would be 70 to 130, right? That's as hard as this gets. The only thing that's going to complicate this thing a little bit, is that this rule that we have, this 90, 99, 90, 95, 99, 95, 68% rule that we have is going to be of limited usefulness to us. I'm going to go back to our little table here, and I'm going to take a look at this. So let's take a look at a couple of the examples we have here. Assume the heights of adult Caucasian men has a mean of 68. I'm going to highlight that. I made it go away. Let me go back here and put the ribbon back. Okay, and a standard deviation of 4 inches. Okay, mean of 68, standard deviation of 4 inches. I told you it was normally distributed. What's the probability that you'll randomly choose an individual that's taller than 68 inches? 50%, right? Mean is 50%. Chances that randomly picking someone that's over 68 inches from that population is 50%. How about between 64 and 72 inches? Well, 64 is how many standard deviations below the mean? One, and one standard deviation above the mean, right? Let's go back to our little chart here. Well, I already told you that between 95%, this is between two standard deviations below and two standard deviations above is 95% of the population. One standard deviation below and above represents 68% of the population. And three standard deviations to the left of the mean and to the right of the mean represents 99.7% of the population, almost all of it. So one standard deviation below the mean, one standard deviation above the mean is roughly 68% of the population. Okay, everybody agree with that? Right, not hard, right? Okay, how about between 60 and 76 inches? Well, how many standard deviations is that below? Two, and above? Two. Okay, so two below, two above. That's what percentage of the population? 95. So between here and here. Notice in this particular diagram, it happens to be a little bit more precise. But for our purposes, I think you can probably get away with just remembering 99.7 and 68 and 95. Assume that the heights of two adult Caucasian women have of Caucasian women have a height of mean of 63 inches and a standard deviation of 3 inches. Mean of 63 and a standard deviation of 3. What percentage of the women in this population have a height that's greater than 63 inches? Again, 50%. Greater than 66 inches. A little bit of a curveball here now, right? Okay, what did I just say here? Let me get the table back here. Okay, so I'm going to draw this distribution. Here's our normal distribution. Okay, our mean was equal to 63. Our standard deviation is equal to 3. So our mean is here, 63. And I asked you what percentage of the women are above 66 inches, right? That's this area in here, right? Well, I've kind of thrown you a curveball, right? Because I don't know specifically what that area is yet. However, I do know that 66 is one standard deviation above the mean, right? And if I were looking to the left of this, one standard deviation below the mean would be 60, right? So I know that the area in here is how much? What's the total area? One standard deviation above 68, right? So if it's symmetrical, what would you expect to be between the mean and this 34%, right? So what percentage of the population is above the mean? That's 50%. So if 50% is above the mean, and I'm not counting this 34%, how much is left in here? 16%, right? Right? 34% and 16% add up to our 50%. Okay? So let's take a look at the next question. Less than 60 inches. Okay, now less than 60 inches. We want to know something. Didn't we say it was symmetrical? Right, so one standard deviation below the mean, I'm looking to the left there. This area is symmetrical to this area, so I can make the same argument here, can't I? 34%, 34%, so that leaves only 16% in the lower half. Right? Good. Okay, good. It'll get a little bit more complicated, but not greatly more complicated. Gestation time for humans has a mean of 266 days and a standard deviation of 25 days. What percentage of pregnancies would you expect to be greater than 291 days? I'm going to sketch this out, and I'm going to wait for you guys to do it, take a second to do it. 291, let's see, 266 and 25. So I'll put this on here. Okay, 266 and 25. Sigma is equal to 25. U is equal to 266. And the question was, what percentage of pregnancies would you expect to be greater than 291 days? Okay, here 200, let's say 291 days is somewhere out here. So we want this area out here. So that looks like it's 25, I hope. It is, right? That's 25, so this is one standard deviation. Right? So we just did that problem, didn't we? Right, same deal, 16%. Okay, what's the next part of that? Next part is less than 241 days. Okay, same deal again, right? 241 days, that's one standard deviation below, that's 25 less. So this would be 16%. Things are about to change though a little bit. Okay. What percentage of the population would we expect to be less than 241 days or greater than 291 days? Less than 241 or greater than 291. Well, both of these ends qualify, right? This qualifies and this qualifies. So 16% chance that it could come from here, 16% chance it could come from here. So the answer there is 32%. Right? 32% chance you might choose one that's someone that a woman that had a baby in less than 241 days or more than 291 days. What if I asked you, what's the probability that you would randomly choose a woman that had a baby between 241 and 291 days? 68, right? Which we could get two ways. One by just subtracting what we know already from 100 or go back and using our rule. Okay, so now I'm going to add a complication. Okay, let's see. Will this add the yeah? This one will give us a little bit of a complication here. Assume that the heights of adult U.S. women have a mean of 63 inches and a standard deviation of 2 inches. I'll draw that again. Mean 62 inches is the mean, and a standard deviation of 2 inches. Okay. What percentage of women you expect to have a mean less than 63 inches? Oh, that's a problem now, isn't it? Right? Okay. What percentage of women would we expect to have a height less than 63 inches? So we know it's more than 50% of the women, right? Because it's the right of the mean, and I'm asking about less than 60, the percentage of women less than 63 inches. So it's going to be the right of the mean, without doubt. Right, so it's going to be more than 50%, but I can't use my rule here, right? Can I? Because what's the standard deviation? How many standard deviations above 62 is 63? Not one. It would have 64 would be one, right? Because standard deviation is 2. It's a half a standard deviation, right? In case it gets complicated, you can calculate the standard deviation, which we usually term Z, is equal to the value you're looking at minus the mean over the standard deviation. So in this case, the value we're looking at is 63 minus 62 over the standard deviation, which is 2. So it's equal to 1/2. Or else you could also look at it as 0.5. Okay, so now we need to know what that area is. But our general rule is not going to help us here. So now we have to go to that nasty formula that we saw. Except we know we're never going to use that nasty formula. We're going to use a table that's based on that nasty formula. Now, you can find any number of these. I put one up on Blackboard, a particular table. Let me get this out of the way. What am I doing here? Oh, that's on there. Okay, I'm going to get to the one I posted on Blackboard was from a book that we used a couple of semesters ago called Agresti. Okay, and the Agresti, all of these tables have a little description or a rule at the top of the table. And that little rule tells you what area, when you look up a z-score, a number of standard deviations, it tells you what area that it's giving you back, so you don't get confused about it. This particular one actually has two tables, because when you have a z-score that's negative, that means it's to the left of the mean, right? Because the value you're looking for is less than the mean. So x minus the mean is a negative number over the standard deviation. I mean, so one standard deviation below the mean is going to be -1, a z-score -1. Okay, so in this case, these are all negative numbers. Then it gives you a second table for all the positive z-scores. Notice that a z-score of 0 represents the mean, which is 50%, right? Makes sense. Okay, but all of the z-scores that are above that are actually to the right of the mean. And the table here, the picture is telling you that the table is going to give you the area from that point of that z-score all the way to the left, right? And this table is going to do the same thing, except it's going to do it for negative numbers. Wherever that z-score like -1 is, it's going to give you the area to the left. So this is going to be more precise also than our original table. So what was our z-score? It was 0.5, right? Positive 0.5. So if I look up a z-score, here's our z-score. I'm going to go down this list, and here is positive 0.5. We happen to have a situation where it's only one decimal point, 0.5, not 0.51, 0.52, or something like that. It's 0.5. If I go over here, each one of these columns represents the next digit, right? So 0.5 is really 0.50. So the area to the left of 0.5 is 69.15%, or 0.6915, if you want to express it as a proportion or a decimal place, a probability, right? So 69.15% of the population is to the left of that value, right? So it kind of answers that question that we had. Now, had we been looking for a z-score of 0.53, we would have said, oh, 0.5 is the first digit, 0, 1, 2, 3. We would have gone down under the 0.03 column, and that would have been 70%, just a little bit more. Okay, everybody get how this table is set up? Right? It's interesting, right? Okay, so let's go back and take a look at the next question. I'm sorry. Sure. Okay, this table, all of the numbers that, you see these z-scores that come down here, right? A z-score of 1 is 1.0. A z-score of 2 is 2.0. A z-score of 3 is 3.0, right? And all these in between represent tenths, right? So a z-score of 1.2 would be 1.2 and the number right next to it. So that would represent 88.49% of the distribution. That's a z-score of 1.2, and this is the area that's represented to the left of that z-score. Okay, now we may want to look up a z-score of 1.28, right? So if we want to look up a z-score of 1.28, we go down to 1.2, and instead of going to the first column, we go over to the 8th column, because 1.21, that's 1.20, 1.21, 1.22, 1.23, 1.24, 5, 6, 7, 8. So the area represented by a z-score of 1.28 is actually 0.9897. So I can blow that up a little bit. Right? Can you see it there? 1.2, or if I'm looking at 0.2, a z-score of 0.2, 0.20 is 57%, 58% almost. 0.2, if I want to find the area for 0.21, it's 0.2 and then under the 0.01, 0.5832. 0.22, 0.23, 0.24. You can look up the z-score to up to 3 digits of precision for the z-score, right? Up to 3.49, right? So that's a lot better than having a single column that goes through 90 pages, right? So they kind of throw it all into one spot. So let's look at the next question on there. Okay, so where was I here? Let's see. Okay, less than 62 inches, but less than 63. Less than 62 is 50%. Greater than 66 inches. Okay, let's take a quick look at what that might be. Notebook. Greater than 66 inches. So 66 inches would be way up here. Oops. Did I unplug here? Oh, I'm using the wrong side. Okay, greater than 66 inches would be up here. Okay, so we're looking at that area there. So between 62 and 66 inches, how many standard deviations is that? 2. Oh, that's actually easier than I thought it was going to be, right? So what's going to be left in this area above 2 standard deviations? What is that? That's going to be, what's that? I'm sorry, where was 6? I'm sorry. So, oh, yeah, we already did that. Didn't we already do that? That this area was, I'm sorry, I guess I didn't make myself clear. That area was equal to 0.05, 69.15, right? Whoops. The area below 63 was 69.15%, right? Or 0.6915. Everybody okay with that? You're not. Oh, no. Oh, no. Okay, I see what you're saying. I completely screwed this up. All right, hang on a second. The mean was 63. Oh, less than 62 inches. Oh, no. Okay. So what's a z-score for less than 62, for 62? It's negative 0.5, right? Everybody agree with that? 62 is negative 0.5? Hang on a second. Okay. The mean for U.S. women is 63. The proportion of women that are less than 63 is 50%, right? The proportion of women that are less than 62 is what percentage? Well, 62 is, if this is the mean, 63 is the mean. 62 is 1/2 standard deviation below the mean, right? Actually, negative 1/2, right? So the z-score I'm looking up is negative 0.05. I didn't hear that. What? Oh, because the standard deviation is 2, right? So 62 is 1/2, is 1 below 63, right? So the z-score is equal to the value you're interested in, which is 62, minus the mean, 63, over the standard deviation, which is 2. So it's negative 1/2, 0.05, right? Because it's half of a standard deviation. Remember now, the mean is 63, right? That's the mean. And the value we're looking at is 62. So we're looking at this area below the mean. Not a great drawing, but we'll have to do for now. Right, so that's negative 0.05. Excuse me, negative 0.5, right? Negative 1/2. So if I go to the table for negative 0.05, now I'm going to use the table that was negative, right? This other table. So negative 0.05, what area does that represent to the left of that value? Negative 0.05 represents 30.85%, 0.3085. Right, so this area that we're looking at here would be 0.3085 or 30.85%. Also, by the way, when we automatically grade the exams, we usually ask you whether to either put the answer in a proportion or a percentage, right? So you might want to keep that when you're doing the exam, just to make sure that it grades correctly if it's automatic grading. Make sure that you put it in the units that we ask for. We almost always go back and check anyway, and we'll correct it if you notice that it's been graded wrong or something like that. But it helps if you get it right the first time. Okay, so I'm going to go on to the next one. Actually, I'm going to ask you guys to do the next one. The body temperature of adults has a mean of 98.6 degrees, right? Pretty clear. Find the probability that a randomly selected individual has a mean body temperature greater than 99 degrees. Okay, that's going to force you to do a couple of things. Greater than 99 degrees and a standard deviation of 0.6. As you're working on it, I'm going to draw it myself. Let me shrink this table down. 90.6. And the standard deviation I said was 0.6. And we want to know greater than 99. So I'm looking for that area over here. Okay, so now I need to find a z-score that represents 99 degrees. Okay. So what is the z-score equal to? Is equal to the value that we're interested in minus the mean over the standard deviation. Okay, what are we looking for? 99 minus the mean, 98.6, over the standard deviation, which is 0.6. So what is that equal to? It's equal to 0.6 over 0.4 rather. 0.4, positive 0.4 over 0.6, which is equal to 2/3, 0.67. I'll call it 0. Everybody agree with me on the z-score there? Positive 0.67. So now, I'm sorry, it was 0.6. See, it's up here. Is it hard to see the screen up here? Because I'm kind of broadcasting this simultaneously. So I could give you a spot to go to where you could look at it on your computers instead of having to look up at the screen, if that'll help. We're running a little late now to switch over now, but next time I'll do that. I'll give you guys a link where you can go to. Okay, so what's my problem here? I want to go to the chart and look up what this area is here that I cross-hatched. What's the first problem that I have? What does my table tell me? What area? It's telling me the area to the left or to the right? To the left, right? To our area always goes from here to the left. Remember how it was shaded? I'll bring the table up again. Right? It always gives you the area. Well, to call to the left, right? Always gives you the area from the z-score to the left. Correct? But what area am I interested in? That area in there. Okay, but we can deduce that because if I look up the area for 0.67, here I'll blow this up a little bit. 0.60123456 right? 0.67 is 74.86, 0.7486, right? So this area to the left is 0.7486, right? That's our proportion there. So what does that leave here? Right, we're going to subtract it from 1, right? If we were using percentage of 74.86, we'd subtract it from 100% because the distribution represents 100% of the population. So this would be 1 minus 0.7486, which is roughly 0.2519 or something like that, 1/4, right? Yes. Let's think about that. In other words, if you had inverted the z-score? No, I don't think so, because it's not really inverted. One's positive, one's negative, right? If we flipped it around, well, actually, what you could do is you could have said, oh, it's 0.67 above. Let me call it negative 0.67. And that area would be the same as this area. And if you look that up, let's give it a try. I mean, it seems a little bit more, it seems like it's more complicated than it's worth, but let's see negative 0.67. Negative 0.67, it works, right? Negative 0.67, you wind up with roughly the same result. 2.1, yeah, right here it is, right here. 0.25. So yeah, you could do that. You could flip it so it's a negative z-score because you're looking for a tail, right? Because then it'll automatically give you left tail. But if you don't want to confuse yourself, you could also do it this way. Okay, so I'm going to move off of this because I want to also quickly cover the binomial distribution. Before I do that, we have the exam coming up next week, right? So I would like to do a review session, most likely either on Saturday morning or Sunday morning. So probably roughly 9:30, 10 o'clock or something like that. So I will record it so everybody can get to it, at some point. But just from a matter of preference, who's better? Well, first of all, number one, nobody wants either Sunday morning, Saturday morning. I understand that, but who would prefer Saturday morning? Okay, who would prefer Sunday morning? It's absolutely practically 50-50. Maybe a little bit more Saturday, but okay, I'll try and like as I said, I usually as the semester goes on, I'll bump these around. Okay, so yes, yeah, I'll definitely record it so you'll be able to get to it as well. Okay, and maybe if I can, maybe I'll do something just to go over the quiz that's left over Monday night or something like that. Like a real brief, something real brief, or maybe I'll just record it and put it up there myself. Okay, so I'll try and set something up for Saturday. Let's see what else is going on. I think that's enough for now. Okay, so now let's talk about this idea of the binomial distribution. Okay, so I'm going to open up Excel. Oh, we got to get through this real quick. I'm going to open up Excel, and I'm going to blow this up a bit. 200%. Okay. So now let's say that we're talking about diabetes. Let's say we have a population. The prevalence of you probably heard this about 11 times already. The prevalence in the population of diabetes is 10%. The probability of picking someone out at random that has diabetes from this population is 10%, right? 1 in 10. If you did it again the second time, 10%. You did it again the fifth time, 10%. It's always 10% because we're taking a random sample. Right now, if you sampled only people from a certain family, that's not random. So you might get, because there are genetic factors involved, you might get a higher percentage or a lower percentage if you just sampled certain portions of the population, right? So, or neighborhoods that might be predominantly one ethnic group or a different ethnic group. You randomly select from that whole population. You can say with some level of certainty that's what my chances are going to be. Okay, so now the interesting thing is that frequently we're called on to try and make a judgment about, well, what about, for something that's binomial, we have to make a judgment about, well, what if I took 100 people? What's the likelihood that I would get 10 out of those 100 people that are diabetic? Say you're running a clinic. You get 100 patients a day, right? You screen 100 patients a day, and you have kits that you give out, instructional kits, like dietary supplements, so on and so forth. For anybody you find that has a blood sugar of 100, let's say that's your judgment on what's diabetic. How do I know what the probability is that I will get 10 people versus 15 people versus 5 people? What are those probabilities? Because I want to have reasonable likelihood without bringing too many of these kits. I want a reasonable likelihood I won't run out of them. But I don't want to bring 100 because that's ridiculous. I know I'll never get 100. What do you think would be the most likely single outcome if you're sampling 100 people and the prevalence is 10%? 10 people, right? You'd expect 10 people would probably be the most likely outcome, right? But the real key is how many would you expect more or less than that? So I'm going to reduce the number there, and I'm going to say you only see 10 patients. I'm going to say, number one, the prevalence is 10%. Okay, 10%, 0.1, right? Same deal. Okay, and I'm going to say the number of people you sample is going to be 10, right? So now I want to calculate what are the probabilities of various outcomes. Okay, so I'm going to say to myself, what's the probability if I sample 10 people that I will get nobody that's diabetic? Well, we had a rule for that, didn't we? Because the probability that they're not diabetic is 0.9. So 10 people would be 0.9 times 0.9 times 0.9. But it's going to be tough to calculate that. We actually have a rule that's called a binomial distribution, that binomial distribution function in Excel. It looks like this, equals binom dist. Now you'll notice that sometimes it comes up with a decimal place, One is a newer way of typing it, and one's an old. Binom dist works fine. And I'm going to put in a parentheses here. Okay, equals binom dist. I left out the D. And as soon as I finish, you can't see this, and I can't blow it up. Maybe I can. No, well, let me blow it up. What you see here is as soon as I put in that parentheses, it asks me for the number of successes. That's the number of people that are diabetic that I'm counting. The number of trials, that's how many people I'm going to sample, 10 in this case. The probability of success, that's the prevalence. And it asks for something called cumulative. And in there, you're going to put true or false, right? Okay, so for now, I'm going to say binom dist equals, let's see, the number of successes is 0, comma, trials is 10, comma, the probability is 0.1, comma, and for cumulative, I'm going to put false. And I'm going to hit enter. The probability of nobody having diabetes is 34%. Okay, what's the probability of one person having diabetes? I'm going to do that here. Equals binom dist, parentheses, and this time the number of successes is one person, right? Having diabetes, comma, trials is 10, comma, probability is 0.1, comma, cumulative again is false. And I'm going to hit enter. And that's the probability that's higher, right? Because it's more probable that you get 1. I'm going to do it one more time for 2. Equals binom dist, parentheses, what was it? The 2 successes, comma, trials is 10 people, comma, probability of success is 0.1, comma, cumulative is false again. Well, I'm about to tell you. Okay, notice it's going down. If I did it again for 3, it'd be lower. If I did it again for so on and so forth, what do you think these would add up to if I did it for all 10? 1, right? Add up to 1, because then we would have taken into account every possibility. Now, what if I asked you, what's the probability of having 6 people that are diabetic, right? Right? Then you would put in here, you would go down here somewhere and you say it's binom. By that time, we'd be down here, dist, parentheses. I'm going to finish up with this very quickly. 6 people, comma, trials 10, comma, probability is 0.1, comma, cumulative, I'm going to put false again, parentheses, and it comes out to a very low probability, right? Less than 100, like 100 to 1%. Okay, now, what if I asked you, what's the probability of having 4 or fewer people that are diabetic, right? Well, let's say, instead of that, let me say 3 or fewer probably. Let's say fewer than 3. Fewer than 3 is 2, 1, and 0. Well, I could just add all of these together, and it would give me that probability. Probability for 0, 1, and 2 people. Well, there's another way for me to do this, and I'm going to do it here. Okay, I'm going to add these together. Equals the sum of these 3 numbers, right? Okay, so I'm going to do this over here. I'm going to say equals binom dist, parentheses, and this time I'm going to say, okay, 2 successes, comma, 10 trials, comma, 0.1 probability, comma, except for cumulative, I'm going to say true. And what's going to happen is Excel is going to calculate the probability of 2 or fewer people having diabetes in your sample of 10 people. Right? So when I hit this, when I enter this, it should come up with the same number as all 3 of these added together. Bingo. And it did, I hope. Yes, it did. If I had asked you 3 or more, it would just be 1 minus this number, right? Get it? Okay. We have to, unfortunately, our evening is over together.